Hello, everybody. I'd like to go through the fundamental concepts in machine learning with math through a book called Deep Learning from Scratch with Building with Python from First Principles, written by Seth Weidman. So, we're going to start with the first chapter, where we're going to have each fundamental concept in the math explained with math in the form of equations, code with little extra syntax in Python, as well as a simple diagram to explain what's going on visually. So first, let's start with the ground level of functions. So functions are different ways to map input to output spaces. So let's define two examples of functions. First, f1 of x, which is taking an input of x and mapping it to an output of x squared, as well as function f2 of x, that finds the maximum between x and 0, meaning that if x is less than 0, 0 will be outputted, while if x is greater than 0, the x will be outputted. To diagram these functions, we can draw an xy plane and then plot many different points for each function and connect the plotted points. We can use Python code in order to create the graph for two functions, where the square function creates a U-shape as the negative and positive numbers for each input lead to the same output. So -1 and 1 squared both equal 1, and -2 and 2 squared both equal 4, and etc. for all the values leading to our U-shaped curve. So that was the f1 of x function, which we previously defined, and the f2 of x function is shown here, where it should be from less than 0 in a straight line across the x-axis, a completely straight line, and if it's greater than 0, it should be a relationship directly between the x input and the output, where the input and output should be the same. So for an input of 2, we will get the output of 2, whereas for an input of -1.5, we should get 0. Another way to depict functions is through a sort of black box definition, where if you put an input through the black box, you get a certain output. So if we put 2 through our square black box, we get 4, because 2 squared is 4. If we put -3 in, we get 9, because -3 squared is 9. If we do the same for our f2 of x, 2 will be equal to 2, as 2 is greater than 0, while -3 will be equal to 0, as -3 is less than 0. Now, before going into the code for functions, I'd just like to, again, cover NumPy, as it is so critical in machine learning. So Python lists usually work by when you add two lists together, they lead to these two lists being concatenated. And if you multiply lists, then you will receive a type error. However, on NumPy, if you add two lists, the corresponding elements are added, and if you multiply them, then an element-wise product is performed. NumPy arrays can also be multidimensional, with columns being axis 0, rows being axis 1, and other dimensions being in a similar fashion. If we want to take the sum of all of the numbers along a given axis, as for example, axis 0 with the columns, or axis 1 with the rows, we can define a given NumPy array with the entries 1, 2, 3, 4 of 2 by 2 shape. And if we add along axis 0, 1 plus 3 is 4, and 2 plus 4 is 6. And along the rows, 1 plus 2 is 3, while 3 plus 4 is 7. Additionally, we can add 2D arrays to 1D arrays through broadcasting and have no errors available. Second, throughout this part of the lecture, I'm going to be using a special type of function called type-checked functions, where each input and output for the function are defined with a specific type. This will allow us to understand easier what's going on inside the code. For example, for a given function called operation, we will have two inputs, x1 and x2, of type NDArray, and output a type of NDArray. Now that we have covered all of these coding basics, the two functions f1 and f2 of x are defined here in code by defining a function that takes an input of a NumPy array and outputs a NumPy array by using the np.power for each element inside of the NumPy array and squaring it to a power of 2. Additionally, for our f2 of x, we can find the maximum between each value of our x. So this should be 0, and the maximum between that 0 and our value of x. Next, I'd like to cover derivatives, which are a method in math that find the slope at an exact point. This is done by usually finding an extremely small number for a given change at that point, and then finding the slope on that. So if we have a given point of a, f of a for a function, we can find the slope between the point with an a value 0.001 less than that and the point f a that is 0.0101 greater than that, and then finding the slope between those 2 points. It's easier to visualize in a diagram. So if we have our point at a, f of a, we can find the slope between a minus 0.001 and f of a minus 0.001, and the slope between a plus 0.001 to f of a plus 0.001. So if we take the slope of those 2 points, we will be able to approximate the derivative at point a, f of a. So another way to visualize this is with our black box, where if we increase 2 by 0.01, what will our output be increased by? We can write code for this by creating a function called derivative, where we provide a given function that takes a NumPy array, an input, also a NumPy array, and a change of 0.001 for a given point. So we can define it by finding the y for both the input, that is 0.001 greater and 0.001 less than our given input point over the change in x times 2, so that way we can find its derivative. So I also like to define a quick terminology here that whenever we say p is a function of e, that means that for a given function, we take an input of e and receive an output of p. Now I'd like to cover nested functions, which can also be called composite functions. This is where we take a given input of x, feed it to one function, then feed the function output to another function, and finally get an output based on the outputs of those 2 functions. So in math, this would be coded as f2 of f1 of x is equal to a given value. And in code, we can create an array function where we have a chained function that contains 2 different functions, and the first will be our f1, and the second will be our f2 inside of that chain. For a given input of x, we can find the f2 of f1 of that x. So the chain rule is a combination of nested functions as well as the derivative, and it allows us to find the derivative of a chained function. This is done by first finding the derivative of the first non-nested function, and then finding the derivative for the outer function based on the output of that first inner nested function. So in a diagram, we could say that the 5-to-1 mapping for our first function leads to a change of, if we change one small unit of 0.001, for example, in our input, it will lead to a change of 3 small units in our output. Then when we do the same for our second function, a change of one small 0.001 in our input will lead to a change of -2 in our output. So if we multiply these, we see that a change of 0.001 in our input leads to a change of -6 units in our output, as when we chain them together, they should theoretically be multiplied as their slopes change in relationship to each other. When we code this, we could create a new function called sigmoid, and then we can find the chain rule for the sigmoid function as well as the square function, and we can code it up for the derivative of our first f1 of x and then the f2 of f1 of x, and we can do it for the square sigmoid and sigmoid square chain. When we plot this, we can see that when we find the sigmoid of the square of x, we can have our slope go down whenever the function itself goes down. Then it goes towards 0 whenever our function starts to flatten, and it goes back up whenever our function goes back up. Similarly, in the square of the sigmoid of x, we can see that our function of the derivative for slope goes up as the slope of our actual function does seem to go up, and it goes back down when the actual function slope does go down. In a slightly longer example, we can also find the derivative for a chain of 3 functions. So f3 of f2 of f1 of x. So we can do this similarly, but for 3 functions instead of 2, and we code this in the same way, now accounting for our third function. And if we do this for our max, x, and 0, sigmoid, and square functions, we can see that when we plot the function and its derivative, the slope stays at 0 at the start, and then it shoots up for our new a greater than 0 maximum function, and it starts to slope back down while the function slope also slows down. Now I'd like to cover functions that take multiple inputs. So for example, we can take an input of x and y and return an output of x plus y. So we could also feed the output of that function to a second function, leading to a nested function including a function with multiple inputs. So when we diagram this, we take an input of x and y, feed it to a function a and receive an output of a, then feed that output to a new function called o and then receive a final output of s. If we code this up, we can see that our first function is x plus y for our two inputs, and then another given function called sigma can be performed on that a to return our final output. Now, for a derivative of functions that have multiple inputs, we can do this by having our previous example with our function with two inputs, x and y, that adds them, has an output, then feeds it to a second function, sigma, to receive our final output, by first taking into account the derivative of the inputs x and y, and then the derivative of the function a of x and y, which is really just the derivative of x plus y. So we can do this for both our variable x and our variable y, and both of those derivatives will be the same. We can code this by first finding the x plus y, then computing the derivative of it, and then performing the rest of our derivative for our multiple inputs function to receive an output. If we have a function that has multiple vector inputs, then this will be taking in two different vectors, which are our one-dimensional arrays, which can be either in the row or column format. And then we could have our vector in the row format and then w in the column format and multiply them together using element-wise product. If we do this, we can represent the diagram in many different ways, including a matrix multiplication box that receives an output, a more detailed diagram taking each corresponding entry into a function, then taking all of the outputs of those into a final function, receiving an output, or we could also take each corresponding entry and then feed it all into one function to receive our output. If we code this up, we can see that if we can just perform the dot product or matrix multiplication between our two input arrays x and w, we will return our function. Then we can find the derivative of this function by finding the derivative of each of our vector inputs, which is done by finding the derivative of each entry inside each vector. So we can see something interesting where the derivative of our vector is actually just the transposition of our vector. So if we have a given vector of w with w1, w2, and w3, the derivative is equal to its transposition, and same for a vector with x1, x2, and x3 entries. We can see that when we code this, all we have to do is just use the np.transpose method, and return that as our derivative. Now, I'd like to take another step further by adding a second function chained onto our function that takes multiple vector inputs. And when we do this, we can first have our matrix multiplication and then a given function of sigma based on the output of that function. Then when we compute the derivative, we can take our derivative of the first function with vector inputs as before, then take the derivative with respect to our new sigma function. When we diagram this, we can see that it's sort of going backwards from our output to the sigma function with respect to our first output, then for the derivative of each of our first vector inputs with respect to our first function. When we code this, we can see that we find the derivative of our function sigma with respect to our input, and then the transposition of w and return the dot product between our two derivative values. We can check if this is right by printing one of our given x inputs, which is a 3x1 vector, and then finding what happens when we increase our last value x3 inside of it by 0.01. When we compute the gradients, when we compute the derivative of our output, we see that it is negative 0.1121 for the derivative for that x3 point. And when we perform further code, we can see that indeed the derivatives we are computing are correct, as that 0.1121 matches what is also shown through other code. Finally, I'd like to show how we can have two matrix inputs to a given function with further nested functions. So we are pretty much taking our vector multiple function example to the next level with two-dimensional matrices. So first, we're going to have a matrix multiplication between our two-dimensional matrices x and w, and then we can feed it through a new function called sigma, and then we can finally sum all of those elements with a final third function. So we can compute the derivative of each of the entries in our final output and then go backwards. So first, let's just pause and look at our function and diagram. So we have our two matrix inputs, x and w, fed into our first function to achieve an output. Then we send it to our second function to receive a second output, and finally through our last summing function to receive our final output. If we code this, we first take the dot product, then take a function of sigma, and then sum all of the elements from the output of that sigma. Then let's compute the derivative of this complete nested function. So first, we can see that we can take the derivative of our first function, of the inputs, then the output of the first function, and then the second function. If we look at the derivative of a summing function, we see that all it is just a matrix of the same shape of all ones. So we can take that and multiply it by the derivative of our first output, which will lead to a complex matrix of shape 3x2. Then we can finally take the derivative of our first two matrices inputs, which is just the transposition. So when we finally multiply all this out, we can show it in code with our first going through the function to receive all the outputs, and then going backwards by having our matrix of ones multiplied by the derivative of our function sigma with respect to our first output, and then times all that times the transposition of our original input. Then we can dot product everything and receive our final output and verify it by creating two random shaped matrices and performing the derivative on them, and then looking at a external derivative and comparing our entry for our first entry in our derivative and seeing that is the same for our output. So overall, this complex derivative function can all be seen as a given input put through a very complex function to show that whenever you change that input by a small amount, our output will change by 0.25 of that small amount, or whatever you can determine based on computing our derivatives. So, for example, if we want to get the derivative of a given point that we have that is indeed changed by 0.25 of however much we change it in the input, we can see that when we plot a line based on the inputs and what its derivative is, it does seem to have a slope of approximately 0.25. So, in conclusion, today we have covered a complete overview of all of the different types of AI, as well as a brief overview of AI as a whole, including machine learning and deep learning. Then we took a deep dive into how to use Python in AI, as well as different basics of Python. Finally, we looked at how the fundamentals of math in machine learning are implemented in different algorithms, as well as how they can be computed. So that is the end of our session.